Ever wondered how animators or motion capture systems create smooth, realistic movements from limited data? What if I told you that a centuries-old math tool, Splines, might be the key to solving one of the trickiest problems in computer graphics? Let's dive into this breakthrough research that's reshaping how we model motion. Traditional methods for tracking movement, like neural networks or ResFields, often struggle with two big issues: spatial coherence and temporal accuracy. Imagine trying to animate a dancer's arm from just a few scattered points. Without proper guidance, the result might look jittery or disconnected. These systems rely on inductive biases, which are like built-in assumptions about how motion should behave. But when data is sparse or noisy, those assumptions can fail, leading to unnatural results. Here's where splines step in. You've probably seen splines in action, those smooth curves used in everything from car design to animation. They work by defining key points, or knots, that guide a flexible, mathematically precise path. The researchers behind this study took that idea and applied it to motion modeling. Instead of guessing how movement should flow, they let the splines explicitly define trajectories, with knots acting as adjustable anchors. The magic happens in how they handle velocity. Traditional methods often struggle to calculate smooth acceleration and direction changes, leading to temporal fluctuations. Think of a robot arm that jerks instead of moving fluidly. This team introduced a new loss function, LV, that analytically derives velocity from the spline's mathematical structure. It's like giving the system a built-in physics engine, ensuring motion stays coherent without relying on complex, opaque algorithms. But how does this compare to existing techniques? Let's break down the results. When tested on sparse data, their spline-based approach outperformed methods like ResFields, achieving a 21% lower endpoint error, EP, a measure of how far predicted motion deviates from reality. They also introduced a novel metric, inspired by Moran's eye, to quantify spatial coherence. Think of it as a smoothness score for motion, which showed a dramatic improvement from 0.79 to 0.96 when velocity was incorporated. What makes this approach truly groundbreaking is its simplicity. By using splines, they eliminated the need for tricky heuristics or multi-stage training processes. No more guessing game, just mathematically sound interpolation. And because the knots explicitly control the degrees of freedom, the system adapts naturally to both sparse and dense data, whether it's a flickering motion capture signal or a high-resolution 3D scan. But here's where things get even more fascinating. While splines tackle motion modeling, another breakthrough in 3D animation is redefining how we handle dynamic scenes. Ever wondered how a 3D avatar can suddenly wear a totally new outfit, like magic? What if I told you it's not magic, but a clever trick called time-variant spatial encoding? Let's unravel how this tech is making animations smoother, faster, and way more flexible. Imagine you're creating a 3D animation of a dancer. Traditionally, changing their outfit would mean manually adjusting every pixel in every frame, a nightmare. But researchers have cracked a smarter way. They use something called a canonical space. Think of it as a blueprint of the scene. This blueprint stores the basic structure of the dancer, like their shape and pose, while separate time layers handle how things change over seconds. Here's the cool part. When you want to apply a new style, say a glittering costume, you don't have to redraw the whole thing. You just tweak the blueprint, and the style automatically spreads across the entire animation. It's like painting a mural on a moving canvas, no messy touch-ups needed. This method is super efficient, cutting down hours of work into seconds. But how does this stack up against other techniques? Let's compare it to Grid 4D, a popular method. Grid 4D works like a grid of tiny boxes, but when data is noisy or movements are wild, those boxes can create floaters, weird, ghostly artifacts. Our TVSE approach. It's more like a flexible net that adapts to motion, avoiding those glitches. It's like switching from a rigid scaffold to a bouncy trampoline for your 3D scenes. Now let's talk about the math behind it. Think of the dancer's motion as a playlist. Each frame is a song. TVSE uses spline interpolation to smoothly connect these songs, making the dance fluid. They also added a smart regulator to keep things stable, even when the music gets chaotic. This means fewer errors and more lifelike animations, whether it's a dancer, a flame, or a spinning pan. The takeaway. This tech isn't just about flashy effects, it's about efficiency and adaptability. From virtual try-ons to real-time gaming, TVSE is paving the way for smarter, faster 3D experiences. And the best part? It's all powered by math that's as elegant as it is practical. Thanks for watching. If you're curious about how these innovations could revolutionize your favorite games or movies, hit subscribe. Drop a comment below. What 3D animation feature would you love to see improved? See you next time.